Hello and most welcome to 1193 of the H series. And today I will look into this book. I will have that in the description as well, by Harald Atmanspacher, Time, Temporality and No. It's a composed book, different authors, one that you would recognize most definitely, and a theme that you will be acquainted by pretty much by now. But it will be incredibly interesting because it's well written. I will start with the very first one, sort of an introductory article by Frederick M. Kronz. Theory and Experience of Time, Philosophical Aspects. Introductory remarks. The concept of time is among the most fundamental elements of the set of philosophical concepts. It has a very rich history and is closely connected with a large, diverse set of ongoing philosophical debates that involve other fundamental concepts such as space, motion, substance, causation, and the infinite and consciousness. It is notorious for leading to philosophic perplexity, despite its familiarity and ubiquitous use in thought, conversation, and action. In addition, it has been examined from a wide variety of perspectives, including the logical, mathematical, physical, metaphysical, epistemological. Sorry, it's a bit warm in here. Psychological, linguistic, sociological, and biological. Those perspectives are by no means mutually disjoint or jointly exhaustive, nor is any of them preeminently philosophical. On the contrary, research on the concept of time from one perspective is enhanced by a familiarity with insights gained from other perspectives. This essay provides a brief introduction to some key discussions of the concept of time in the history of philosophy from the time of Aristotle to the beginning of 20th century. It will focus on the views of 6 major figures: Aristotle, Newton, Leibniz, Hume, Kant, and Mach. Certainly, there are other major figures whose views on time are worth considering, such as Plato, Plotinus, Augustine, Locke, Bradley, MacTaggart, Bergson, Husserl. 6 figures were chosen in order to strike a proper balance between breadth and depth, and those figures in particular in order to facilitate the development of 2 specific themes. One asserts that a substantial part of the confusion surrounding the problem of characterizing the nature of time was due to a failure to appreciate and to satisfactorily resolve the tension existing between metaphysical, mathematical, and empirical aspects of time. The other asserts that as the awareness of this tension and the desire to resolve it grew, so did the relative importance of the empirical aspects, which became the predominating one of the free by the beginning of 20th century. The essay concludes by indicating some of the key problems of empiricism and the relevance for furthering our understanding of the nature of time. So we start with the first one, and that is Aristotle. Aristotle's broad-ranging views on the nature of time. Aristotle's writings on time serve as a natural starting place for the following reasons. Prior to the emergence of the philosophical thinkers in ancient Greece, time was often personified in quasi-mythical cosmogonies. A fairly common character was Chronos, a substitution for Kronos, the father of Zeus, and there are many examples in which time is a figure of might who is generator and ruler of the cosmos. The representation of time in ancient thought was gradually transformed from personification to mathematization, beginning with the writings of the pre-Socratic philosophers such as Anaximander, Empedocles, Pythagoras, Parmenides, Zeno, Heraclitus, Democritus, and culminating in the writings of Plato and Aristotle, the preeminent philosophers of that period. Unfortunately, all that remains of their writings are fragments and somewhat unreliable reports of their teachings in later writers. Those fragments and reports have been collected together, and around that collection has arisen a formidable body of highly specialized and technical literature involving much speculation. Aristotle's view on time was the predominating view for centuries. Those of Plato lacked the breadth and depth of Aristotle's and were considerably less influential. Aristotle discusses time throughout the Physics. The most important discussions occurs in Book 3 to 4, with the most concentrated discussion occurring in chapters 10 to 14. The following list summarizes some of the major themes concerning time that emerges in physics. 1. Listen carefully now. I would say this is the best exposure of Western time, as it were, in the beginning ever. Very nice summary. 1. Time is a measure of motion, and this means that A. Time actually exists, only if motion exists, and B, time actually exists only if a measurer exists, where C, a measurer, is a conscious, rational agent that is capable of counting. 2. Time is not identical with or reducible to motion, since A, regular motions can be used to measure time, but time is not a measure of itself. B, motion can actually exist without a measurer, and consequently without time, and C, motions can vary from one thing to another at different places and times, but the passage of time is the same everywhere for all things. 3. The present moment actually exists. The past and future only potentially exists. Moreover, A moment is like a point-like temporal entity. B, time is not constituted of moments, since a part must measure the whole. C, the past and future are infinite, because there is eternal motion. D, the present moment separates the past from the future. Four, time is a continuous flux, since a motion is a continuous flux. Moreover, space is infinitely divisible, but not infinitely divided. And C, time is infinitely divisible, but not infinitely divided. 5. There is only one time. And A, the elements of time are ordered with respect to before and after, because B, there is only one universe. The above list is not intended to be exhaustive, but it does represent the most important themes concerning the nature of time that were put forth by Aristotle. The first of the 5 major themes posits a crucial link between time and the perception of motion, and that is indicative of a tendency toward empiricism in Aristotle's thinking. The second thesis is primarily ontological. It says that motion and consciousness are ontologically prior to time. That is to say, the former are elements, the latter are a construct. The rest are primarily mathematical and are indicative of a tendency toward rationalism in Aristotle's thinking. In each of the 3 types of cases, empirical, ontological, and mathematical, there are other elements present. For example, in the empirical case, there is a reference to counting, which is arguably a mathematical operation. In addition, the themes are rather eclectic, ranging from common sense to abstract idealization. There is substantial tension between the empirical and mathematical themes. Aristotle's analysis of the concept of time is primarily empirical. Since it is founded upon the perception of motion. But the punctual nature of the present, the infinite divisibility of time, and the infinite extension of time into the past, the future, seem to be beyond the bounds of experience. One might try to analyze those notions of potential infinity in terms of processes of dividing and traversing, but it seems that such an analysis must involve other notions such as perpetual, eternal, endless, everlasting, and permanent that seem to be just as irreducible to experience as the potentially infinite. Clearly, finite but indefinite is too weak to capture Aristotle's intent. In any case, given Aristotle's rejection of Platonism, and specifically his rejection of separately existing realm of forms, it is difficult to see these mathematical notions as idealizations. When then is his basis for countenancing them? It is difficult to say, even in light of his detailed discussion of motion in the latter half of the Physics. Nevertheless, it does seem clear that it would not be appropriate to regard them merely as convenient fictions with no ontological consequences, given his rejection of atomism, which is based on arguments for the infinite divisibility of matter, space, and motion. Three, Newton on absolute time. That's the chap we recognize, I think. The Aristotelian system was the predominating cosmology for centuries. Among the first to offer important and influential alternatives to it were Galileo and Descartes. A new concept of time was not elaborated by either of them, but it must be emphasized that although Galileo's leanings were predominantly empirical, the conception of time that he presupposes in his empirical studies were predominantly mathematical. The irony is compounded by a brief remark by Descartes, who was very much a rationalist, in which he maintains the core of the Aristotelian notion of time, that it is a measure of emotion. The mathematical motif that was implicit in Galileo's writings is elaborated in Newton's. Like Aristotle, Newton was primarily an empiricist. He also was concerned with the empirical, ontological, and mathematical aspects of time. But in the famous scholium following definition 8, at the beginning of the book 1 of the Principia, Newton explicitly characterizes two different notions of time, absolute time and rational time. Newton regards the former as mathematical, the latter as empirical. He explicitly attributes ontological status to the mathematical notion, which makes his view as puzzling as Aristotle's, given his strong leanings towards empiricism. Later, he seems reluctant to reify some of his mathematical representations of time, but it is difficult to explain what underlies that reluctance ultimately. The scholium is an addendum to Principia. It's not really an actual part of it. It is not temporally same. The scholium does not make clear why Newton regards absolute time as mathematical, since he merely says there that everything exists in it, that it flows equally without relation to any motion, and that the order of its part is unchanging. This is peculiar because it is those issues that have a mathematical character, whereas the features that he mentions appear to be based primarily on common sense. Even more peculiar are his empirical arguments for the existence of absolute motion in the scholium, which are supposed to serve as indirect support for the existence of absolute space and time. He asserts that two globes bound by rope are in absolute rotation if and only if there is a tension in the rope. And this is so whether or not there are other bodies present in the understanding in the universe. If there are no other bodies, the rotational motion or lack thereof can only be with respect to absolute space. Presumably the same is supposed to go for time, but even granting that there would be motion with respect to absolute space, it is not clear that the motion would have to be with respect to absolute time, since it seems that the motion could serve to measure itself. If a spring scale is used to measure the tension in the rope, in any case this argument is crucial and will be returned to several times below. Well, it's to do with the inertial point of reference, the much discussed thing ever in any discussion about an absolute start of measurement of time and space. for some insight concerning the mathematical properties that Newton ascribed to absolute time, it is best to have a brief look at the earlier works of Newton and other parts of the first edition of Principia. Later it will be necessary to examine Newton's change in attitude towards some of those properties in his later writings, including some important differences between the first edition of Principia, published in 87, and subsequent editions that appeared during Newton's lifetime. In the Gravitione, an unfinished work that very likely preceded his work on Principia and may have been written during his student days at Cambridge, Newton was more explicit about the nature of time. In that work, he says that time is eternal because time is an immanent effect of God and God is eternal. He indicates that each moment of duration is the same at each part of space, thereby indicating that time involves the idea of absolute simultaneity. Finally, he says that the parts of time derived their individuality from that order alone. But he does so without indicating what a moment is or whether moments are part of time. Since these are metaphysical and mathematical aspects of time rather than empirical aspects, it is rather likely that these are regarded by Newton as features of absolute time. In the October 1666 tract on fluxions, Newton presented his results on his research on the calculus, which he worked on during the previous 2 years. The use of O as an infinitesimal unit of time explicitly plays a crucial concept role in that essay. He regarded time as passing with a steady flow, and that enabled him to regard the fluxion of a quantity as the rate at which the quantity changes with respect to the uniform flow of time. Thus, if P and Q represents fluxions of the flowing quantities x and y respectively, then the expressions PO and QO represents moments of x and y. The moment of quantity responds to the infinitely small increment of the quantity that is generated in a moment of time, O. Thus infinitesimal quantities are eliminated. Some more. By reduction using fluxions and an infinitesimal unit of time. De Morgan reports in his essay on the early history of infinitesimal in England that in the first edition of Principia, moments were understood as infinitesimally small quantities and were used throughout. But in the second and third editions, most arguments involve relations that are only true in the appropriate limit. The explanation of this difference is Newton's growing skepticism about infinitesimal quantities, which became manifest in his De Quadratura Curvarum, a work on the foundations of the calculus, which was begun around 1691 and published in 704. In that work he attempts to eliminate infinitesimal quantities in favor of a limit notion. It is curious that he almost made the work a supplement to the second edition, but abandoned that idea at the very last minute. It is even more curious that even in the third edition of Principia, there are passages such as in example 1 of the corollary of the proposition 10 of book 2, when Newton continues to make use of an infinitesimal quantities. Both occurrences are suggestive of some ambivalence as to whether he saw the limit approach as the true one. If it is assumed that Newton held a view of time that was relatively constant from his student days until he began to rethink the foundations of his calculus, then the views expressed by Newton concerning time in various works prior to 1691 can be summarized in the following table. Time is an eminent effect of God, and A. Time is eternal because God is eternal, and B. Time exists whether or not motion exists, and C. Everything exists in time. 2. Moments are parts of time, and a moment is an infinitesimal unit of time. B. The order of the parts of time are unchanging, and C. The parts derive their individuality from their order alone. 3. Time flows equably without relation to any motion, and A. Motion is a continuous flux, so B. Quantities have movements, infinitely small increments. 4. Time is linear, since a time is ordered with respect to before and after, and B. Each moment of duration is the same at each part of space, meaning that C. There is only one time. It's getting more interesting. I need to fill up some coffee. Theses 2 through 4 are primarily mathematical in character. The first thesis is primarily ontological, but clearly has a substantial mathematical consequence: the infinity of time. The second leaves some important issues unaddressed, For example, Aristotle asserted that a part must constitute a measure of the whole. Is there a sense in which infinitesimal measure a finite length? If so, that needs to be explained. If not, then it is not clear why temporal points of zero length should not be regarded as paths in Newton's sense, or why Newton's notion should be referred to Aristotle's. Although Newton is careful to distinguish between an empirical and a mathematical notion of time, it is puzzling that he should give ontological preference to the mathematical notion given his strong empirical leanings, which are reflected in his four methodological precepts of the Principia, given his repeated pronouncements against the use of hypotheses, that is, propositions not obtained by induction from experience. Except for his argument to show that absolute acceleration has observable effects, which was characterized above, it seems that a relational theory of time, such as the one advocated by Leibniz, one of Newton's chief antagonists, would be a more suitable alternative. So, let's get into the antagonist, Leibniz. Leibniz's relational theory of time and his criticism of Newton. Leibniz's views on time, which are abstracted from the famous Leibniz-Clarke correspondence, are very close to those of Aristotle. Indeed, it would not be misleading to say that Leibniz's account is an elaboration of Aristotle's, since they share so many theses concerning time in common. As with Aristotle, there is a close tie between time and motion, but they are clearly distinct notions. Leibniz says that time is merely a relation of objects with regards to succession, and that succession requires relative motion between two things, i.e., it requires a continual change in the distance between two things. There is also a tie between time and perception, though Leibniz's view does differ somewhat insofar as he holds that motion must have observable as opposed to observed effects. This difference is questionable, since what Aristotle said could be interpreted that way. Concerning the present moment and the infinity of the past and future, Leibniz agrees with Aristotle that only the present moment and instant, which he says is not part of time, presumably because it does not measure the whole and therefore is likely to be a temporal point, exists. Unlike Aristotle, he implies that time is not eternal, since the world has both a beginning and an end. Nevertheless, there are some subtle and important differences. One key difference between them is that Leibniz uses two metaphysical principles: the principle of sufficient reason, PSR, and the principle of identity of indiscernibles. To ground his system of philosophy, he regarded them as great principles that would change the state of metaphysics by making it a real and demonstrative science, and used them in a variety of different contexts. Including his discussion on the nature of time. The principle of identity of indiscernibles asserts that there are not in the nature two indiscernible real absolute things, or that two completely similar substances are identical. The principle of sufficient reason asserts that all truths have a reason why they are rather than are not. Leibniz indicates that a reason for a truth must show why that truth contributes to making this world the best, suggesting that final causality plays a crucial role for him as it does for Aristotle. Samuel Clarke, an advocate of the Newtonian ideas of absolute space and time, suggested in the famous correspondence with Leibniz that this same world could have been created earlier in absolute time than it was. Leibniz counters, asserting that there would be no reason for God to choose one time rather than another to create the universe, asserting that there would be no choice since all possible creation times are identical. Clarke responds by accepting, asserting that God would have a reason, and by questioning the status, asserting that the points of time are distinct. Clarke also points to the type of inertial effects discussed by Newton in his thought experiment, involving the two globes to make a case for absolute time and space. Leibniz responds cryptically and, as a result, ineffectually that the source of inertial effects are in the bodies themselves, and consequently that those effects need not to be referred to absolute space and time. Thus, the metaphysical stratagems of Leibniz are unconvincing. He took the empiricist stratagems of Hume and their effective implementation by Mach to develop what came to be regarded as a devastating reply to Newton's thought experiment. Five. Hume's empirical analysis of time. Hume, like Newton, was an empiricist. His empiricism was strongly motivated by the success of Newtonian mechanics. In section 1 of the Enquiry concerning human understanding, he asserts his intent to apply the Newtonian method to discover the rules governing the operation of the mind. It is striking that Hume's views on time, which are fully expressed in part 2 of book 1 of his treatise concerning human nature. Hume explains that all perceptions to the mind, including sensations, emotions, feelings, thoughts, judgments, etc., have their source in experience. They are divided into two classes, impressions and ideas, which are distinguished by their degree of force and vivacity. The perception invoked when recalling the pinprick 3 weeks later is an idea. Each idea was either preceded by a corresponding impression or can be analyzed into parts, each of which was so preceded. Hume asserts that the latter type of idea is formed by the imagination through its abilities to compound, transpose, augment, or diminish ideas of the former. This analysis is applied to space and time and leads to the following views. Since the capacity of the mind is limited, it is not possible for the mind to form an adequate conception of the infinite. There is a lower limit on division into parts and an upper division on additions to extension. One way to produce a sensation of an indivisible length is to put a dot of ink on a wall and then recede from the wall. At some distance from the wall, the distance will depend on a variety of factors. The dot will not be visible, but moving one step closer will bring the dot back into the visual field. The resulting sensation is an indivisible length. Such lengths have a finite measure in the sense that placing two end to end results in a length that is double the original length of either of them. Hume suggests that similar considerations hold for time. That is to say, he held that time must be composed of indivisible moments having a finite measure. This is the first of two major themes that Hume asserted concerning the nature of time. The second makes change a necessary condition for time. An interval of time, or duration, is a succession of moments. It is derived from a perceivable succession of perceptions, meaning that each element in the sequence differs from its predecessor in some perceivable manner. The time interval is nothing more than the perceived order of the succession of differing perceptions. Contrary to Hume's expressed views, it does not appear that there are perceived moments of time as there are perceived indivisible lengths. he does not present a temporal counterpart to the example involving the ink dot, and it is difficult to imagine one. The empiricist Newton seemed to have had it right insofar as he emphasized the flowing aspects of time. Another difficulty with Hume's point of view is that it is entirely subjective. But it seems that experienced time has an objective aspect that Hume does not try to explain or even acknowledged. The flowing aspect of experienced time is emphasized in the writings of Bergson and Husserl, which are not discussed. The objective aspect is discussed by Kant and is tied to the notion of causation. Six, Kant on the empirical reality and transcendental ideality of time. In his Transcendental Aesthetic, Kant explains that time is an empirically real and transcendentally ideal a priori intuition. Time is an intuition, not a concept, because concepts are multiply instantable, but there is only one time. It is infinitely extendable, but not infinitely extended, and infinitely divisible, but not infinitely divided. It is empirically real in that all experiences are in time. It is a priori because it is a subjective condition. That is a condition of the subject. That is a prior condition for all experiences. That is to say, time is not merely the observed order of sequence of observationally distinct perceptions. Rather, it is the subjective condition that makes such an ordering possible. The a priori status of time is also crucial for Kant, because it serves to make counting possible and thereby provides a suitable basis for arithmetic. Finally, time is a transcendentally ideal in that it is nothing whatsoever in reference to what is outside the bounds of experience. Put in a short break here, I'm sorry. Kant regards Newton's views on time as metaphysically extravagant. That objection is weak given his superficial treatment of Newton's two-globe argument. He substitutes the two globes in Newton's universe with a single rotating sphere and claims that the rotation would have observable inertial effects because there is relative motion between the center of the sphere and its other parts. Perhaps that is what Leibniz had in mind. In any case, the response does not mesh well with his view that matter is infinitely divisible, but not infinitely divided, and does not work for a rotating ring. Kant rejects Hume's views on grounds that there is an objective succession of appearances that cannot have its source in perception, and because it does not provide a proper foundation for arithmetic. His account of the objective succession of appearances occur in the famous second analogy in the Critique, and is based on the view that causality is an a priori concept of the understanding whose function is to order objectively the sequence of perceptions given by the sensibility according to a rule. That ordering makes possible the perception of motion, so time is more fundamental than motion for Kant. Finally, he rejects Leibniz's views because they are based on the assumption that there is an isomorphism between things in themselves and appearances. Mach's critique of Newton, say we're talking about Mach in Swedish or German, and the influence of Machian empiricism. Kantian rationalism and Humean empiricism were the two predominating philosophers of science in the 19th century. In the writings of William Whewell, a predecessor of Mach, and the first philosopher of science to base his philosophy of science on a thorough study of the history of science, and regarded by some as being the father of historiography of science. The Kantian influence is hard to miss. So in his originality as a philosopher, his notion of consilience of inductions had a profound impact on Darwin, and it has much insight to offer with regards to how to think about the relationship between physical theory and physical reality. That notion and related themes are discussed briefly later in assessing Mach's view. Empiricism became the predominating influence of the development of philosophy, of science and physics in the first half of the 20th century. The most influential proponent of empiricism in the 19th century was Ernst Mach, whose philosophical writings had a major impact on Einstein. Einstein says in his autobiographical notes that the type of critical thinker required for discovering the central point needed to clarify and then to resolve a paradox was decisively furthered by reading the philosophical writings of Hume and Mach. The paradox turned out to involve absolute time in a crucial manner, and its resolution ultimately led to Einstein's discovery of the relativity of simultaneity, a consequence of the theory of relativity, which was first developed in his article on the electrodynamics of moving bodies. The Machian influence is clearly present in the introductory paragraphs of that essay, where he affirms the adequacy of appealing only to relative motions and in the kinematical part of the essay, where he affirms both the conventionality of the travel time for one-way trip of a light beam from one place to another, and the relativity of simultaneity for distant events. The success of relativity was a major factor in the institutionalization of empiricism and led to the formation of the Vienna Circle, which was formed in the early 20s around Moritz Schlick and consisted primarily of formal, natural, and social scientists with strong empiricist leanings. The institutionalization of empiricism also influenced Heisenberg in his student years and later in his development on quantum mechanics during the mid-20s, which no doubt served to bolster the empiricist movement. By the late 20s, the influence of Carnap and Wittgenstein led to the formation of with an official name, philosophy, and a set of goals. That group was the Verein Ernst Mach. Its philosophy, logical positivism, and its goal to become the driving force behind an international movement. By the early 30s, it was organizing important international congresses and developing influential publications in which the philosophical program was elaborated and applied. It was extremely influential throughout the 40s and 50s and began to wane in the early 60s. Mach was the first to construct what was seen as a decisive criticism of Newton's argument for the existence of absolute motion from the inertial effects of rotational motion. His criticism involves two principles, a verification principle and an inertial principle. The verification principle asserts that a judgment has scientific significance if and only if there is some observable phenomena that is relevant to determining whether that judgment is true or false. Since there is no way to set up an experiment involving a universe with only two globes joined by rope, the claim concerning absolute rotation is not scientifically significant. A Newtonian could respond by asserting that Newton's assertion about what would happen in the hypothetical universe is a straightforward extrapolation from what happens in the actual one. Mach forestalls that response by introducing an alternative inertial principle that is observationally equivalent to Newton's as long as there is sufficient number of bodies that are practically fixed with respect to one another, sufficiently massive and distant, and appropriately distributed. Observational equivalence is relative to the available data, meaning in part relative to the existing technology. That is to say, it may eventually be possible to construct a crucial experiment that decides in favor of one of the two inertial principles. Until then, pragmatic considerations such as simplicity give the edge to Newton's inertial principle over Mach's. That is to say, the issue is a matter of convention, not confirmation. Remember that. What is most important, however, is that it will always be possible to formulate an observationally equivalent alternative to the inertial principle that wins favor at any stage. Thus, it will never be possible to establish what will happen in the hypothetical world, that is, absolute motion and absolute time cannot be established as scientifically significant in the manner suggested by Sir Isaac Newton. Aside from the critical component, Mach's views on time had an affirmative component. It must be had an affirmative component. In several publications he contrasts physiological time with physical time. Physiological time is the time sensation experience, of which he offers a brief but suggestive remarks that fall under three categories: phenomenological characterization, evolutionary biological accounts, and physico-chemical conjectures. Those remarks are, for the most part, summary statements of the work of other writers of that period. Physical time is what is obtained when mathematical and metric concepts are applied to physical processes, and the result is a refinement of time sensation that serves as a useful tool or an economically efficient means to organize sensations and to regulate behavior. From an ontological point of view, those benefits means nothing. The world consists only of our sensations. The representation of time as a continuum, for example, is scientifically significant to the extent that it facilitates the development and use of physical theories that are in agreement with experience, but that could never suffice to give it ontological significance. Although Mach's stance may be quite reasonable with regards to inertial principle and the temporal continuum, there are other cases where it is too extreme. To the extent that sensations are inescapable theory-laden is the extent to which Mach's position cannot be metaphysics-free. Also, there are theoretical constructs that the majority of scientists do not and will not fail to reify, such as amoebas, DNA molecules, hydrogen atoms, electrons and neutrinos. Thus, Mach's empiricism must be mitigated. Whewell suggested that when several seemingly unrelated phenomenological laws are subsumed under a theoretical law that has ontological significance, when several seemingly unrelated lower-level theoretical laws are subsumed under another theoretical law that has much greater ontological significance. Both situations are cases of what we will call a consilience of inductions. At what level of generality are we justified in assuming that the theory reflects the underlying nature of physical reality? It is difficult to say, but it is clear that the empiricist solution of giving ontological significance only to sensations is too simple-minded. It is best to approach that question, as with some more specific questions concerning the nature of time, from a variety of perspectives, including that of the experimentalist as well as that of the theorist, and hope to gain some deeper insights. Perhaps Einstein's very deep insights concerning the nature of time, such as the relativity of simultaneity and the resulting need to replace the independent realms of space and time by space-time, are or soon will be generally regarded as being beyond question. Other matters, such as whether Heisenberg's uncertainty relations are fundamentally in the same way, whether there must be a time-energy uncertainty relation to complement the position-momentum uncertainty relation, whether time must be represented as an operator in addition to, or even rather than a parameter, are far from being regarded as characterizing other aspects of the true nature of time. Yet it does not seem that such matters are forever outside the bounds of theory-laden experience. That is to say, it is reasonable to suppose that there are some features of time that can be settled within a more sophisticated version of empiricism, one that is subtly mitigated by theory and practice. So we jump from that. Well, it's not a big jump. We are almost in time. Mach is in the 1920s, and I will start here by an article about quantum mechanics and time there. And it's called Delayed Choice Experiments and the Concept of Time in Quantum Mechanics by Shimon, Malin, Department of Physics and Astronomy, Colgate University. Abstract. Delayed choice experiments seem to have a puzzling feature. The present seems to change the past. This is shown to be a result of the paradigm in which such experiments are described. In particular, it is shown that in a description which is based on the philosophy of A.N. Whitehead, this puzzling feature does not occur. The puzzle. To introduce the puzzle presented by delayed choice experiments, we need to invoke the quantum mechanical principle of superposition. This principle states that if a quantum system, such as an electron or a photon, is presented with two alternatives, it will not choose between them. It will enter a state of superposition of the two alternatives. For example, if a photon entering an apparatus is presented with two possible paths to follow, path A and path B, it will enter into superposition of the two paths, a state in which it can be said to be the following partly path A and partly path B. This will occur provided no observation is made as to which path was taken. If such an observation is made, a state of superposition is no longer possible, and the photon will be found either along path A or along path B. A delightful explanation of the principle of superposition is contained in Robert Gilmore's book Alice in Quantum Land. Alice entered the wood and made her way along a path which wound among the trees until she came to a place where it forked. There was a signpost at the junction, but it did not appear very helpful. The arrow pointing to the right bore the letter A, and that to the left the letter B, nothing more. "Well, I declare," exclaimed Alice in exasperation, "that it is the most unhelpful signpost I have ever seen." She looked around to see if there were any clues as to where the path might lead, and when she was a little startled to see that Schrödinger's cat was sitting on the bough of a tree a few yards off. "Oh, cat," she began rather timidly, "would you tell me, please, which way I ought to go from here?" "Well, that depends a great deal on where you want to get to," said the cat. "I'm not really sure where," began Alice. "Well, then it doesn't matter which way you go," interrupted the cat. "But I have to decide between these two paths," said Alice. "No, that is where you are wrong," mused the cat. "You do not have to decide. You can take all the paths. Surely you have learned that by now. Speaking for myself, I often do about 9 different things at the same time. Cats can prowl around all over the place when they are not observed." "Talking of about observations," he said hurriedly, "I think I'm about to be obs." At that point the cat vanished abruptly. The puzzle of delayed choice experiment is one of many quantum mechanical puzzles. In the sequel we'll comment about 2 other puzzling aspects of quantum mechanics. 1. The violations of Bell's inequalities. They seem to show the existence of superluminal propagations of influences. 2. The riddle of the collapse of the quantum states. In spite of strenuous efforts for the past 70 years, there is no convincing mechanism for the choice involved in a collapse. The fact that things seem strange often indicates the need for a paradigm shift, like the cat. It is a characteristics of a paradigm shift that what was inexplicable in the old paradigm becomes simple and obvious in the new. Consider, for example, the fact that if one keeps traveling east, one comes back to the point of origin. This fact, which is puzzling in the flat earth paradigm, indicates the need to shift to a paradigm of spherical earth. Can we see the direction of a paradigm shift that will make the seemingly strange feature of delayed choice experiment simple and obvious? Whitehead's philosophy, a historical perspective. During the 20s, when quantum mechanics was being discovered, Alfred North Whitehead introduced in his book Process and Reality a revolutionary paradigm which he called the philosophy of organism, and is now usually called process philosophy. As we shall see, this philosophy is in remarkable agreement with the findings of quantum mechanics. Whitehead, working at the Harvard University, was aware only of the old quantum mechanics of 1900 to 1915. He was unaware of the discoveries of Heisenberg, Born, Jordan and Schrödinger. This makes the agreement between his paradigm and the findings of quantum mechanics all the more remarkable. Strangely, the confluence between Whitehead's process philosophy and quantum mechanics was noticed only in the 60s. The seminal paper is by G.M. Burgess, 63. Among the others who worked on the relationship between Whitehead's philosophy and quantum mechanics are A. Shimon, Henry Stapp, and myself. Malin. My paper, Whiteheadian Approach to Bell's Correlations, contains references to earlier work. Some of the main ideas. As the name philosophy of organism indicates, Whitehead's paradigm is one of an alive universe, one in which creativity and experience are fundamental to the universe and to everything in it. This may sound like cheap New Age stuff. In fact, Whitehead was one of the most rigorous thinkers of his century. Before he turned to philosophy, he was a mathematician, a co-author of Principia Mathematica, the rigorous thinking of an outstanding mathematician is evident in Whitehead's magnum opus, Process and Reality. One basic idea of Whitehead's philosophy is this: the fundamental building blocks of the universe, the atoms of reality, are not enduring objects, but what Whitehead calls actual entities, or throbs of experience. Actual entities can be characterized as follows. They are neither purely subjective nor purely objects. They have both subjective and objective characteristics. 2. They do not endure in time. They flash in and out of existence in space-time. The apparent existence of enduring objects is due to many collections of actual entities coming one after the other in quick succession like frames in a movie. 3. Each actual entity is a nexus of relationships with all the other actual entities. 4. An actual entity is the process of its own self-creation. 5. This self-creation involves accommodating and integrating within itself. This is comprehending or prehending in Whitehead's terminology all the previous actual entities as settled facts that cannot be changed, and all the future actual entities as potentialities. This process of self-creation involves a sequence of phases which are delineated and analyzed in detail in Process and Reality. An example: listening to an orchestra playing a symphony involves each moment accommodating the sounds produced by the orchestra. This accommodation depends in turn on many collections of past, actual entities, such as previous knowledge and training in music, association with the symphony, etc. Notice that at each instant there is one experience. The end product of the process is a new actual entity, one throb of experience. The fundamental building blocks of the universe are, then, elementary experiences. We do not live in a universe of objects, but in a universe of experience. 7. Subjectively, that is, for itself, an actual entity is a pulse of experience. The end of the process of self-creation is called the satisfaction of the actual entity. Its subjective existence is momentarily. Objectively, that is, for other, future actual entities, it is a settled fact. For others, it's a settled fact, that is. The fact that it did happen cannot be erased. The end of its private life is its perishing, is the beginning of its public career. 8. The point that is crucial for our purposes is this: the process of self-creation of an actual entity is not a process in time. It is rather a atemporal process leading to the momentary appearance of the completed actual entity in space-time. Quoting Whitehead, in the process of self-creation, which is an actual entity, the generic passage from phase to phase is not physical in time. The generic process is not a temporal succession. Each phase in the generic process presupposes the entire quantum. Alfred North Whitehead. 3. Atemporal processes. That'd be interesting. Let us pause to examine the idea of an atemporal process. This idea is strange for us because we are used to the Newtonian paradigm of a clockwork universe. We've spoken about that before. A clock is somewhere never designated with a place or how it works, but it's still there somewhere, in which everything happens in space-time. However, the idea of an atemporal process is not an invention of Whitehead's. It goes back at least to Plato. All of Plato's dialogues are based on the distinction between that which always is and has no becoming, and that which is always becoming and never is. That is the distinction between the world of immutable being and the world of generation. The universe consists of both. Plato's account of its creation, the Timaeus, is an account of creating first the world of immutable being, and second, the world of generation. The world of immutable being has nothing to do with time. It is just not only unchanging, but also by its very nature unchangeable. The concepts of time and change do not apply to it. Equally, sameness, difference, beauty, justice, all of the other forms are of this nature. The soul of the universe, too, is eternal, and yet Plato describes it in considerable length, the process by which the soul of the universe is created. Clearly, it does not mean creation as a process in time. Indeed, we read about the creation of soul, forms, and much else besides, before we get to the creation of time. Processes that are outside time are central to Plato's thinking. As far as the account of creation goes, they are the essence of the story. A confinement of the account of creation within time would be unthinkable. But this notion of atemporal processes is necessary not only for the big story of the creation of the universe. Atemporal processes are, according to Plato, all around us. They are the essence of any process of becoming. A beautiful object becomes beautiful through its participation in the form of beauty. This participation is not a process in time. It is rather an atemporal process that leads to the appearance of a beautiful object in space and time. One person who was deeply influenced by Plato in general, and the Timaeus in particular, were Heisenberg. Quote from him: "Quite often it happened that after spending the whole night on guard in the telephone exchange, I was free for a day, and in order to catch up with my neglected schoolwork, I would retire to the roof of the training college with a Greek school edition of Plato's dialogues. There, lying in the wide gutter and warmed by the rays of the early morning sun, I could pursue my studies in peace." End of quote. 4. Whitehead's philosophy and quantum mechanics. Now we're coming into the interesting. According to Heisenberg's interpretation of quantum mechanics, quantum states represent potentialities, some of which are actualized in acts of measurements. So the quantum mechanical universe is an interplay of potentialities and actualities. So measurement brings about, through the process of the collapse of a quantum state, what John Wheeler called an elementary quantum event. Such an event is a flash of actual existence as soon as it appears out of the background of potentialities. It disappears back into the background of potentialities. This concept of elementary quantum events is remarkably similar to Whitehead's concept of actual entities. According to both quantum mechanics and Whitehead's philosophy, reality is not made of enduring objects, but of flashes of existence that disappear as soon as they appear. The main difference between actual entities and elementary quantum events is that the latter have no subjective aspects. They are completely objective. This is due to the fact that quantum mechanics, like all of our science, is based on what Schrödinger called the principle of objectivation. Quote from Schrödinger: by the principle of objectivation, I mean what is also frequently called the hypothesis of the real world around us. I maintain that it amounts to a certain simplification which we adopt in order to master the infinitely intricate problem of nature. Without being aware of it, and without being rigorously systematic about it, we exclude the subject of cognizance from the domain of nature that we endeavor to understand. We step with our own person back into the part of an onlooker who does not belong to the world, which, by this very procedure, becomes an objective world. Schrödinger's point is similar to Whitehead called, in his book Science and the Modern World, the fallacy of misplaced concreteness. When I look at a tree, the statement, "there is a tree out there," is an abstraction. The concrete fact is that I see a tree out there. And now it's becoming too interesting. That's it, I'm going to put a pointer here. Well, it's a rather heavy lecture, but we passed from going, see where we are in time here. We've gone all the way from Aristotle. We follow the empiricist movement from Aristotle, then going to Newton, the antagonism of Leibniz, and then we ventured into David Hume, and then Kant. So we see here it's a change, is thesis, antithesis, and synthesis. So new things gets established. And neatly, the first history is following the sort of fork in the road. Remember Alice in Wonderland or Quantum Land? When she has a choice between A and B, this is definitely A. A is in Aristotle. And then we end up with Ernst Mach / Einstein and the establishment of the relative and the general theory. the general and specific theory of relativity. Sorry, just a bit hazy here after all this lecture today. The other path, the second with Malin here, goes in a quite different direction. It seems to start with Plato and then makes a jump all the way to 1900s and to 1915, where Whitehead started to develop his process idea. And a process is taking what is real as the foundation. And of course in quantum mechanics, as in neurology, a tree is not a real fact. It's an abstraction. Could be served some purpose. It is not unpractical, but it's not something in the world. And you should understand this by now. This is the 1193 lecture. But if you think that there are trees out there, you are badly mistaken. None of the philosophers will be taking up the last couple of hundred says anything to that like. It would be adverting to something purely metaphysical, unprovable, as in not possible to falsify, to use a term from Sir Karl Popper. It's hugely abstract. It's still usable, but never ever possible to consider as being a thing of reality. Newton assumed that, but he never explained how it could be real. So instead he constructed his time and space around this unthinking problem. So he never mentioned it, he never realized it. Neither did Hume, neither did Kant, Leibniz. I think he could have a Q if it would continue with its monads, but he didn't. Mach certainly did not, and Einstein we know did not. It is the establishment of these people, the fork A, that leads to the existences that so badly trouble science today, that sort of fills up everything and has led us to abandon the path B that I think we sometimes were taking. This is a very good metaphor in a way, because we can take both paths. But we are more and more abandoning path B. That's the path of quantum mechanics and Whitehead, where what is real is what we experience, not what metaphysically been assumed to be the case, all the way from the pre-Socratic Parmenides, Xenophanes, Anaximander, Anaximenes, and so forth. Only question by Heraclitus is now established as being of reality, almost like a sect where everybody is looking in the same weird direction. But we know from neurology, when people are speaking about objects, perceiving them, which is impossible, their fMRI scans, the functional magnetic resonance inference scan, are not showing much of a perception. It can actually be shown. Whereas people who are acutely aware and upright and in balanced state, like a football player or a tennis player or whatever, I really like the idea of Roger Federer. It's no happenstance that he is a professional tennis player. He perceives things. We can see that people of his kind, high in sports, they do have perceptions. And perceptions is not something God-given to everyone. It is something that people develop in different degrees. But today, the most common thing is that perception is incredibly low. Therefore, this is shutting off perception. We know as a fact, and this has been proven so many times, Ian McGilchrist called this the deadening of life, or the taking away of perception. Normally people are like this when they perceive. There cannot be no perception or there can be no thinking. And therefore you assume something subjectively only connected to your emotions. And here comes Wittgenstein once more, something you cannot even understand yourself. This is the trying to create a private language. Let it be the Esperanto of the body, also a useless constructed language that doesn't work. Or is it even worse? In this case, you don't know what time and space and scale are. You are abandoning life itself. You are letting the fire, as Heraclitus calls it, be extinguished. You are like the piece of salt in the sea, slowly being dissolved. This is the posture of that. Tension and anti-tension. Anti-tension is collapse. Anti-tension is the sofa, is the chair, is having tremendous tension all over the body and tremendous flaccidity all over the body. This is the body-mind system trying to maintain contradictions, because if there is no reality, no perception, we have to construct an alternative matrix, so to speak. We have to go into the Aristotelian fantasy world and construct objects, and those are constructed via contradistinction, by keeping in our body a distinction between empty space and what contains, and forcing the body, the perceptive system, to eat of its own joints. And this is called by Immacul's the representational mode, that you see, so to speak, only your own representations. When we talk about reality today, we're talking about representations, because this is the default way of perceiving the world. In a way shared by, we all put ourselves in the same quantum state, this one, and thereby reinforcing disstability, reinforcing lack of understanding, reinforcing lack of knowledge and thinking. But we never do the same thing. We can never live in the same classical world. The classical world is everyone living in their own shut-off world from perception. That's the only chance of maintaining an anti-quantum mechanical life world, a way of life. Because it's not an ideology, it's a way of life. It's a way of cutting off everything that joins you to the world, which is the body, cutting you off from localizing yourself. Instead, you think you are an origo. According to Newtonian, you have that bench 1.5 meters in front of me, and you think you can orientate yourself by using the Newtonian GPS. And then you left everything of your existence behind. You become a phantasm, having no real connection to the world. And then you can, as John Searle said, assume that you are a brain in that. That cannot be assumed. It's a false paradox in the quantum world. It's an impossibility. I think this will strive to be very interesting. I'm looking forward to looking more into Alfred North Whitehead. I only bordered to his ideas before. And the process model by Gendlin is similar in some instances. But he has very strong argument for having a philosophy of quantum mechanics. And do not forget, we should say hooray, hooray, hooray. Now we have a quantum mechanics as a Nobel Prize taker. This is a huge success for science once more. I think I should end there. And I say thank you very much. Have a very pleasant afternoon. Bye bye for now. Sorry, have a pleasant morning. It's still 11 o'clock.